Hi, it's time for another math easy solution. Turn discuss further into hyperbolic functions and look further at the catenary and more specifically asymmetric catenaries. And now we're going to go over a formulation for determining the parameters of asymmetric catenaries or just the catenaries in general. So first of all, recall from my earlier video that an asymmetric catenary is still in the shape of a catenary, and also want to point out it is very useful to obtain a formula that allows for determining the parameters of an asymmetric catenary, such as the vertical and horizontal distances between the endpoints, the length of the cable, and physical properties of the cable represented by the A term. So if we can get a formula that includes all of these, that is very useful for design and engineering and otherwise. So first of all, let's just consider the following. I'll draw a XY axis like this and draw a asymmetric catenary. Let's say the first endpoint's low like here, and then we go to this point across, and then let's say the lowest point intersects at the y-axis. So we get something that looks like this, and then goes up like that. So yeah, so we have this shape like that, and then recall that the equation of a catenary, asymmetric or regular symmetric one, is still going to be a cosh x over a plus a constant c. And now let's say that this point right here, this is at x2, and I'll write this one as x1 like that, and here is at x2, and I'll write this as y2. That's the coordinates of that point. And then the coordinates of this point, this is going to be x1 and y1. So yeah, those are the coordinates. And now when we want to look at, well, the vertical distance, the vertical and horizontal distance between the endpoints, the vertical distance, I'll draw this in red. It's going to go across somewhere like this. And this vertical distance, I'll call this v, where this goes just all the way across to there. And now the horizontal distance is just from here all the way to here. And this is h. Yeah, and now the length of this cable is another property we need. I'll just go from here, and then you just get the whole length across there. That's L. Yeah, so we have here now three of these variables for the engineering properties, as in like where do you want to place the endpoints and so on, how long the cable, and then the and then the physical properties of the cable in terms of the tension and weight density is all encompassed by this A parameter, as explained in my earlier videos. Yeah, so now what we want is to determine a formula that includes all of these, just so it's easier for design and engineering and so on. So first thing we'll do is, well, the horizontal distance, we know that one right away. That's just going to be, well, h equals to just the difference x2 minus x1 like that. And in this case, x1 is negative, so when you subtract, you're subtracting a negative becomes a positive, and so then you're adding it like that. So this is what h is. We'll plug this in later on in this video, so keep it there. Now the vertical distance v is equal to, well, let's just difference y2 minus y1. So v equals to y2 minus y1, and then we can plug these inside this formula, this a cosh x over a plus c. So now we have a cosh x2 over a plus c, and then subtract this by, put this in bracket, a cosh x1 over a plus c. And those constants just cancel. We'll have a minus 1 here, and what we're left with is equal to a cosh x2 over a minus a cosh x1 over a. Alright, so that is what v is equal to right there. Yeah, so now let's go further. So basically the idea is I'm just going to try to write these out in terms of the catenary formulas, just to see what we can work with. And now the next thing we're going to do is look at the length for L right here. So we wrote v, h, now we just need L. So recall from hyperbolic, from my earlier video, hyperbolic functions catenary example 4, which I looked at arc length, that the arc length or length of a catenary cable is as follows. For just a regular symmetric catenary, what we have is, if we just draw this out like this, is x, this is y, and the symmetric one has the same heights across like that. I'll just draw it like that, like a smiley face mouth. And in that video earlier, so then this, what we had was this distance is going to be negative b, and this one is going to be b. It's the exact same distance across from the origin. And now the length across here, this one is going to be, well, L. Let's write this L, and this equals to 2a sinh b over a, or hyperbolic sine of b over a. But notice the 2, that just means we're doubling, we're just 2 timesing the distance from the origin to either one of these sides. It's perfectly symmetric like that. Yeah, so thus in our case for an asymmetric catenary, what we get is, well, we have it like this. Here, this is going to be our x, this is our y, so we have the lower distance or lower height there, higher height there. It goes across like that. Now this horizontal distance from here to here, this is our x2, this one is x1, and now what we'll do is, well, this distance across from here to here, this one is L1, and now from here to here, this is equal to, well, L2. And the total length is going to be, well, L equals L1 plus L2. But we know that, well, L2, this is an easy one, is just positive over there. It's going to be half of this. So that's going to be 2a sinh b over a, but b is now x2. So this is going to be a sinh, now we write x2 over a. So that is L2. And L1, this is going to be equal to, well, the absolute value. We're going to assume a is constant. We'll just do absolute value because we're going to deal with negatives in there. But we need to deal with the absolute value of this because we're going to go on the negative side there. So this equals to a, absolute value of a sinh x1 over a. And the reason we put absolute value is because again, sinh of a negative is going to be negative. So recall that sinh or sinh of a negative variable, negative theta, for example, equals to, now using the definition of sinh or hyperbolic sine, is equal to e to the power of, well, now we have a negative theta, minus e to the power of negative. And now we have that negative theta like that over 2. This becomes here, that becomes e to the positive. So we'll then move that in the forward one. So we have e to the positive theta. We'll do plus like this. E to the positive theta, and then this is going to be plus e to the negative theta. Just move it onto the other side so it's easier to see the identity. And now we can take the negative out. That equals to negative e to the theta minus, that becomes negative e to the negative theta like that over 2, and this just equals to a negative sinh, and that was just the definition of sinh theta like that. Yeah, so what we get is a negative one, and for positive values of theta it's actually positive. Yeah, recall, I'll do a graph video later on. But so what do we have now? This equals to, if we have it absolute value, this equals to negative a sinh x1 over a. Yeah, that's because x1 is less than 0 there. And also note again that sinh theta is greater than or equal to 0 for theta is greater than or equal to 0. And hence that's how we get rid of the absolute value. So we get a negative of this negative one like that, and it's less than equal to 0 for theta is less than equal to 0. And in fact equals to negative of that. Yeah. So let's put it over there. Yeah, so thus what we have is a total length is going to be L equals to L1 plus L2. So we have L equals to L1 plus L2. So I'll write L1 over L2 first so we could have a minus there like that, so it's neater. So a sinh x2 over a, this is going to be our L2, minus the a sinh x1 over a like that. When we account for the absolute value and put a negative because it's negative for negative x values. Yeah, so right, so now that we have all this together for L, I'm just going to circle this one out like that. So that's the L value. What we could do is we could write a useful expression of all of these parameters as follows, and that is in fact doing L squared minus v squared. And I actually got this from Wikipedia page on catenaries. Is very interesting there. And this expression they use, so L squared minus v squared, or the length of the cable squared minus the vertical distance squared, equals to, now when we go plug in our v value, where is our v? V is the a cosh x2 over a minus that. And the reason they're doing squared is because we can use some useful identities, and then minus this one over here. So that's actually L squared first. Let's do the L one first. So L, yes, sinh x2 over a minus a sinh x, x1 over a. Now we're going to square this and then subtract this by the v is the same thing, except it's just, remember, it's just cosh. Is the same exact thing, but we're dealing with cosh instead of sinh. So we have a cosh x2 over a minus a a cosh as well, like that, cosh x1 over a squared, like this. So we're going to square that. So now we can just use the FOIL method and expand the top one. The top part is going to multiply this by itself. That's going to be a squared sinh x2 over a, and then this times it by this, so we're going to get a sinh x1 over a times it by, well, another a is going to be there as well, so we square that, a sinh x2 over a. And then what we'll do is we'll multiply this by this. That's going to be exactly the same thing, so we just add another 2 and it's going to be negative. And then next one is going to be, this multiply by itself, the negative becomes a positive, and then positive a squared sinh squared. Oh yeah, I forgot to square this one. Yeah, I forgot to square that. Now we have a x1 over a. Yeah, like that. And now we'll do the exact same thing for this part over there. So we'll do a minus and put in a bracket a. This one multiplied by itself, we're going to have an a squared cosh squared x2 over a, like that. And then minus this by this is going to be again a squared cosh x 1 over a cosh x2 over a, and then this by this is going to be the exact same thing. We'll add another 2, and then we'll have now the last part here. This adds together a squared cosh squared x1 over a, like that. And now first thing we notice is, well, this one here we could use the basic hyperbolic trig identity for this one to simplify this one and this, because we have a sinh squared and a cosh squared, and these are the same constants in front, a squared, like that. So what I'll do is, well, recall that cosh squared theta minus sinh squared theta equals to 1. And now in this case we have a minus the cosh one, so we just put a minus on both sides. So we'll have a minus cosh, put a square like that, yeah, minus cosh squared theta plus sinh squared theta equals to negative 1. So the only difference for our case, like that. So thus what we have is, putting these together, what we get is an L squared minus V squared equals 2. And now what we have is over here we could just factor out the a squared. So we'll do a squared, and then combine these ones, we'll have a negative, or just put a sinh forward. So sinh squared theta minus cosh squared, yeah, the theta is in this case x2 over a minus cosh squared x2 over a, yeah, over a, like that. And then put that in bracket. Now the next one is actually, I'll ignore this middle one for now. Let's do this one first, and then do the other one after, just because it's the exact same thing as this one or similar. So we have a plus a squared, and now this one, combine this, put this bracket. Now when we put the negative, that's going to be negative there. So we'll have again sinh squared x1 now instead of x2 over a minus sinh squared x, actually not sinh, that's cosh right there. So cosh, like this, cosh x2 over a. Actually, x1 again. It's just a bit confusing. So it's going to be x1 over a. Yeah, like this over there. So just, yeah, I got a bit confused. Write this a bit neater. Yeah, like that. So what we have now is, well, this is just this formula right there, that identity. We can see that proof in my earlier video. So this is going to be equal to, well, this whole part is equal to -1. This one's also the exact same thing. That is equals to -1, like that. Yeah, but we're not done with this whole entire expression. Now we have these ones we're gonna combine. And now what we'll do here, but to simplify, because we have a negative and a negative there, I'm just gonna take this bracket out and then put a negative there, put a positive there, switch everything, put a negative like that. Again, to make this one look more easy. And now what we're gonna do is we're gonna take out 2a squared, so factor that out, and again, then we're gonna add a 2a squared to this formula, because we're not done with this part when we combine the two. So 2a squared, and then this is a positive side, so we have now a cosh x1 over a, cosh x2 over a, and now we are subtracting by the sinh side of that. So we have minus sinh x1 over a, sinh x2 over a, like that. And now this is another identity we could use. So first of all, recall the other identity in my earlier video, and hence why I did a bunch of hyperbolic trig identities in my earlier videos, or earlier recent videos. So now recall this identity that we have cosh, and if we have an x minus y like that, this equals to just cosh x cosh y minus sinh. So we go from sinh to, from cosh to sinh. Now sinh x, sinh y, like that here. So thus in our case here, this part all the way here equals to, now we have, this is going to be, well, x1 and x2, and now we're going to, it's yeah, exactly the same thing here. We're going to minus the sinh like that. So this equals to cosh x, x1 over a is our x variable. We'll switch them. So x1 over a minus x2 over a. But again, it doesn't matter which ones you choose. You could just move this one in the front or this one in the front. Doesn't matter. So we could. This is the same thing as writing cosh x2 over a, and I'll write it like this instead because it's a bit easier to handle, because we could replace the x2 minus x1 with h. So it's the same thing. We could use it for either one like that. So that's what we have there. So that's what we have. Finally, when you put this all together, now we can simplify this. S is -1, and this is a squared. So that means we have L squared minus V squared equals to negative, and you can combine those. So -2A squared, and then plus this whole thing over there, plus 2A squared, and then this is going to be, and we'll use this one instead. So this is going to be 2a squared cosh x2, and what I'll also do is just that's the same common denominator. That's the same thing as writing x2 minus x1 over a, both of them over a, like that. And now finally we could factor out the 2a squared. So this equals to 2a squared. Move that over to the other side, cosh, and now this x2 minus x1, that's just h. So this whole thing, that's just equals to our horizontal distance x2 minus x1 of the catenary. So now what we have is, and I'll put a bracket like this, cosh of h over a, and then minus, yeah, we took this one out, so that's going to be -1, like that, and moved it over to the other side. So this is a pretty neat formula. But we're not done yet. Recall from my other video on the double angle trig identity, for cosh. So the corollary number 2 actually of that video. So recall cosh 2 theta equals to, well, this just equals to 1 plus 2 sinh squared theta. So because we have this -1 there, and we want to get rid of it, because notice here we have a 1 plus 2 sinh squared theta, as I showed in my earlier video. So make sure to watch that and put that in link in the description below. Because if we move this over, then we have a cosh -1, and then equals to just one term. So in this case, what we'll do is, well, let 2 theta equals to this h over a, so we have a cosh with this one there. So then what we have is this theta is equal to now h over, we'll move this 2 on the other side there, so 2a like that. So then what we get is a cosh of a h over a, cosh of h over a, and I'm going to move this 1 to the other side, minus 1 equals to, equals to 2 sinh squared. Now theta is equal to h, h over 2a like that. Put this a bit neater, so sinh, and then this is going to be h over 2a like that. So that's what we have. Now we're going to throw this inside this formula there, throw it over there, and then we're going to throw that back down, and what we end up getting is, so thus what we have is an L squared minus a V squared equals to, when we move this over there, this is going to be a 2 times it by, there's a 2 there, so that becomes 4 a squared sinh squared h over 2a like that. And now we could expand this even further. We can expand this even further by square rooting both sides like that. And now this L squared minus V squared, that's always going to be positive because the length of the cable, it's going to be sagging, and it's always going to be bigger than just that vertical distance, just by using even basic trigonometry, basic Pythagorean theorem, even if it's a straight line. So this is always going to be positive, and we don't need to worry about plus or minus on these square roots. We're dealing with positive numbers here. So when we do this, what we end up getting is finally, this becomes L, I'll put the square there. L squared minus V squared equals 2. Now this 4 square root of 4 is 2. Square root of a squared is a, and now we just get rid of all that. Sinh squared is gone. Now we have h over 2a like that. So now we have one formula that includes all of these parameters. L squared, we have L, we have the length of the cable, the vertical distance, we have the horizontal distance, and we have the physical properties in terms of tension and the linear weight density of the cable, all in one interesting formula. And now, according to Wikipedia, to the Wikipedia page of the catenary, this specific formulation for the parameters of the catenary is a transcendental equation. You can see my earlier videos on transcendental functions, because it just means you can't solve it using basic functions. We'll have to use some numeric stuff like that, or just a numerical approximation approach to solving these. And here's from the Wikipedia page. This is a transcendental equation in A and must be solved numerically. It can be shown with the methods of calculus that there is at most one solution with A is greater than 0. So there is at most one position of equilibrium. And also want to make a note, if V equals to 0 and H equals to 2B, then we just get the length of a regular symmetric catenary. So if we go over here, that's the formula like that. So if V equals 0, so the vertical distance is 0, which is the asymmetric catenary. So we'll have L squared minus 0 squared. 0 is just that's the V squared is just equal to 0. So this equals 2, and then on the right side we have 2a sinh, and now the h1, if it equals to 2b, so that's exactly symmetric one like that. 2b, that's the horizontal distance of a symmetric catenary, divided by 2a like that. The 2's cancel here, and then this becomes, that's a 0. Square root of L squared is just L, so we get an L equals to a 2a sinh, sinh, and then we have a b over a. This is the same formula I explained in my earlier video on example 4, and then I noted above, which is just the length of a catenary, or just a symmetric catenary. So 2a sinh b over a, and that's a way of double checking our work. That's correct. Anyways, it's all for today. So that's a very useful one. It's a pretty extensive video. Hopefully you followed along, but notice all this extensive algebra, manipulation, trigonometric identities, and we get finally this nice, neat little package there. That's again, it's a transcendental equation. Can't use basic functions to write it as, so you got to do some numerical approximations to obtain those values. Anyways, it's all for if you learned, and like always, you guys want to show that that length of the line. So we have this one here, and again, as I explained, L equals 2A sinh B array. Very interesting. And going all the way back around to do it. Anyways, all for today. Like always, you can download these exact notes in the link below, as well as viewing these notes on Steemit. And make sure to check out my math forums and go and post whatever cool math or science stuff you find. Anyways, all for today. Thanks for watching, and stay tuned for another Math Easy solution.